Third International Physics Olympiad, year 1968, IPHO. Problem number 1. Figure shows a mechanical system consisting of 3 carts A, B, and C, of masses M1 equal 0.3 kg, M2 equal 0.2 kg, and M3 equal 1.5 kg respectively. Carts A and B are connected by a light taut inelastic string which passes over a light smooth pulley attached to the cart C as shown. For this problem, all resistive and frictional forces may be ignored, as may the moments of inertia of the pulley and other ends of the wheels of all 3 carts. Take the acceleration due to gravity G equal to be 9.81 meters per second square. First question. A horizontal force F is now applied to cart C as shown. The size of F is such that cart A and B remain at rest relative to cart C. A. Find the tension in the string connecting carts A and B. B. Determine the magnitude of F. Part 2. Later, cart C is held horizontally while cart A and B are released from rest. A. Determine the accelerations of carts A and B. B. Calculate all the tensions in the string. Solution for problem number 1. First, we have to find what is the acceleration of all 3 carts. That will be F over mass of all 3 bodies. Now, using this equation, we can find what is the acceleration of cart B and A, because acceleration for cart B equal A, and for acceleration A equal G. So that will be M2A equal M1G. And from here we can find that A from one end it's equal to M1 over M2G, and from other hand it's F over M1 plus M2 plus M3, and from here we can find what is F. F equal this expression, which is 29.6 newtons. Now we can find what is the tension in our cord. That will be M1G, which is 2.94. So that was a solution for questions A and B, part 1. Question 2. Now, because our body C is not moving, from one hand that M2A equal N, and from other hand we have M1A equal M1G minus N. It means that if we add these 2 accelerations, we can get that total acceleration for all wheels equal M1 over M1 plus M2G, which is 9.89 meters per second square. And after that we can find what is our tension. That will be M2A, which is M1 M2 over M1 plus M2G, and that's equal to 1.19 newtons. So that was a solution for all problem 1. Third International Physics Olympiad, year 1969, IPHO. Problem number 2. Water of mass M2 is contained in a Cooper calorimeter of mass M1. Their common temperature is T2. A piece of ice of mass M3 and the temperature T3 less than 0 degrees Celsius is dropped into the calorimeter. Question A. Determine the temperature and the masses of water and ice in the equilibrium state for general values of M1, M2, M3, T2, and T3. Write equilibrium equations for all possible processes which have to be considered. Question B. Find the final temperature and the final masses of water and ice for M1 equal 1 kilogram, M2 equal 1 kilogram, M3 equal 2 kilogram, T2 equal 10 degrees Celsius, T3 equal negative 20 degrees Celsius. Neglect the energy losses. Assume the normal barometrical pressure. Specific heat of cooker is C1 equal 0.1 kilocalorie per kilogram 1 degrees Celsius. Specific heat of water C2 equal 1 kilocalorie per kilogram by 1 degrees Celsius. And the specific heat of ice is C3 equal 0.462 kilocalorie per kilogram by 1 degrees Celsius. Latent heat of fusion of ice L equal 78.7 kilocalorie per kilogram, and take 1 calorie equal 4.2 joules. Solution for problem number 2. Here we use the following notation. Let T be the temperature of the final equilibrium state. T0 equal 0 degrees centigrade, the melting point of ice under normal pressure conditions. Big M2 equal to final mass of water. Big M3 equal final mass of ice. And M2 prime less than M2 mass of water which freezes to ice, and M3 prime less than M3 mass of ice which melts to water. So here we can discuss 3 different options. So first option is when final temperature greater than 0 degrees centigrade. It means that all ice and the water became water. The other possibility when everything became to ice, when T less than T0. And also we have possibilities when final temperature equal to T0 and part of ice, let's say that's M3, became ice and the other is water. So let's see what happened in each cases. First case, suppose that everything became water with a temperature greater than T0. It means that if we put here on the left side all heat which was taken from water and the calorimeter, we have T2 minus T multiplied by C1 M1 plus T2 minus T multiplied by C2 M2. This is all heat which was taken. On the right side we have ice. So first ice became to 0 degrees. It means that here we have T0 minus T3 multiplied by C3M3. That's total heat from ice from temperature T3 to temperature T0, plus all heat was taken to convert our ice to water, which is L multiplied by M3, plus the rest, which is T minus T0 multiplied by C3 and M3. This is heat what was taken to final temperature T. Second case, this is the opposite. So now we suppose that everything became ice. So it means that on the right part of this equation we have T minus T3 multiplied by C3M3. This is total heat what was given to ice, and that's equal to temperature of a calorimeter, T2 minus T multiplied by C1M1, plus the same for water from temperature T2 to T0, C2M2, plus temperature which was taken from water to converted to ice, which is LM3, plus the same for ice, which is T0 minus T multiplied by C3M2. So that was second case. And third case is when everything became in temperature T0. In that case we have from left side all heat what was taken from water and calorimeter to get zero temperature. That's this one. And from other hand we have the same thing for ice, which was taken from, which was given from temperature T3 to temperature T0, this one, and plus change of heat what was created due to change of mass M3. So here we have, if mass M3 became less than mass big M3 became less than M3, it means that part of this ice go into water, and in other case we got more ice. So it means that in this case we can take in account masses M3 from 0 to M2 plus M3. In other case it's not convenient. So let's see what happened in each cases. If we get data from part B and try to put them in our first and second equation, we will get a solution which are not allowed. So it means that in the first case we cannot get temperature less more than T0. In this case we cannot get temperature less than T0. So it means that only possibility is third case. In third case we have this equation where we have to count everything except M3, because all other data are given. So from here we can find that this equation, and if we solve it m big 3, we will get this equation, which is 2.11 kilogram, which is a little greater than the initial 2 kilogram. It means that part of water became ice, but this is still less than initial 1 plus 2, which is 3 kilograms. So it means that this is the correct answer. So M3 belongs between 0 and 3 kilograms. So that was the solution for problem number 2. Third International Physics Olympiad, year 1969, IPHO. Problem number 3. A small charged ball of mass m and the charge q is suspended from the highest point of a ring of radius r by means of an insulating cord of a negligible mass. The ring is made of a rigid wire of a negligible cross-section and lies in a vertical plane. On the ring there is a uniformly distributed charge big Q of the same sign as small q. Determine the length L of the cord so as the equilibrium position of the ball lies on the symmetry axis perpendicular to the plane of the ring. Find the first general solution for particular values. Big Q equals small q equal 9.0 multiplied by 10 power negative 8 coulombs, R equal 5 centimeters, M equal 1 gram, epsilon 0 equal 8.9 multiplied by 10 power negative 12 farads per meter. Solution for problem number 3. In equilibrium, the cord is stretched in the direction of the resulting force of G equal mg, and the force F equal Q multiplied by electric charge E in x direction, where x is stands for the electric field of the ring on the axis in distance x from the plane of the ring, because perpendicular direction equal to 0. Using the triangle similarity, one can write that tangent theta, which is x over r, equal QE over mg. Now, because all charges from our ring distance L from our charge Q, total charge will be this one multiplied by sine theta, because it's in x direction. So from here we can find that cosine theta equals R over L, or this expression, and now L equal cubic root from this expression. After putting numbers, we will get 7.2 multiplied by 10 power negative 2 meters. That was a solution for problem number 3. Third International Physics Olympiad, year 1969, IPHO. Problem number 4. A glass plate is placed above a glass cube of 2 cm edges in such a way that there remains a thin air layer between them. See the figure. Electromagnetic radiation of a wavelength between 400 nanometers and 1150 nanometers, for which the plate is penetrable, indicate perpendicular to the plate from above is reflected from both air surfaces and interferes. In this range, only two wavelengths give maximum reinforcements. One of them is lambda equal 400 nanometers. Find the second wavelength. Determine how it is necessary to warm up the cube so as it would touch the plate. The coefficient of linear thermal expansion is alpha equal 8.0 by 10 power negative 6 negative degrees Celsius. Interactive index of the air N is 1. The distance of the bottom of the tube from the plate does not change during warming up. Solution for problem number 4. Conditions for the maximum reinforcement can be written as 2dn minus lambda k over 2 equal k lambda k, for k equal from 0 to 1, 2, etc. Here, because we are losing half of wavelengths due to reflection for the, so we have this equation. But because n equal 1, we finally have 2d equal 2k plus 1 multiplied by lambda k over 2. So here we have d is thickness of the layer, and we assume that n equal 1 and k is maximum of order. Let us denote that lambda prime equal 1150 nanometers. Since for lambda equal 400 nanometers, the condition for maximum is satisfied by the assumption. Let us denote that lambda p equal 400 nanometers, where p is an unknown integer identifying the maximum order for which lambda p multiplied by 2p plus 1 equal 4d. The equation yields that for fixed d, the wavelength lambda k increases with the decreasing maximum order k, and vice versa. According to the assumption that lambda p minus 1 must be less than 1150 newtons, but lambda p minus 2 must be greater than 1150 nanometers, we have this inequality, which can give us next inequality. We assume here that now instead of p we have p minus 1, and here we have p minus 2. Now substantiating to the last inequalities 4d, that we have these two inequalities. Here we have lambda p equal 400 nanometers and lambda prime equal 1150 nanometers. So we can subtract everything by 400 nanometers and we have these two inequalities. Now we can count both separately, that from one hand we have p must be greater than 31 over 30, but from other hand it must be less than 77 over 30, and both of them give us p equal 2. And now we can denote that lambda 2 equal 4d over 5, which is 400 nanometers, and from here we can find that total length d equal 500 nanometers. Now we can find what are lambda 1 and lambda 0. For lambda 1 we have that's equal to 4d over 3, which is 666.7 nanometers, which is good because it's less than 1150, and lambda 0 equal 4d over 1, which is 2000 nanometers, which is greater than 1150. It means that we solve this problem, because next maximum will be for 666.7 nanometers. And the last thing is to find what is change of our temperature, because total dL equal alpha multiplied by L multiplied by delta T. Here we have a delta L equal 500 nanometers. Alpha, that's our coefficient of enlargement. L is our 2 centimeters, and delta T we have to find. So that will be delta L over alpha L, and after putting numbers we have 3.1 degrees Celsius. That was a full solution for problem number 4.